Imagine stepping onto a scale tomorrow morning and seeing double your weight. Not because you changed, because the ground beneath you did. This is Earth, but twice as wide. Same rock, same iron core, same oceans, just bigger. And that one difference changes everything about your life, your body, and whether humanity ever leaves the surface. Right now, you weigh about 75 kilograms. On this bigger Earth, you'd feel every single one of 150. Not carrying a backpack you can take off, not a temporary burden. This is your weight, from the moment you're born until the day you take your last breath. Your heart is the first thing to notice. It was designed to pump blood upward against 1G. Now it's fighting 2. Every beat works twice as hard to push blood to your brain. Stand up too fast and the world goes dark. Your circulation can't keep up. Fighter pilots experience forces like this for seconds at a time, wearing pressure suits that squeeze their legs to keep blood from pooling. You'd need that kind of help just to get through breakfast. Over years, your heart would thicken. Not in a good way. The walls of your ventricles would grow dense and stiff, struggling to relax between beats. Cardiologists have a name for this: hypertrophic adaptation. On our normal Earth, it's a medical condition. On this one, it's just Tuesday. Your bones would change too, not overnight, over generations. The human skeleton would become denser, thicker, more compact. Your spine would compress. Vertebrae would flatten. The average person might stand about 1.3 meters tall. Children wouldn't grow tall and slender. They'd grow wide and strong, like wrestlers, even the ones who never exercise a day in their lives. And something you do every day without thinking, walking, would become a calculated effort. Each step lands with twice the impact. Your knees, your ankles, your hips, all absorbing double the force, thousands of times per day. Running would feel like sprinting through deep water. Jumping, you barely clear the ground. But humans are adaptable. Let's say we survive. Let's say we build a civilization on this heavier world. What does it look like outside? Step outside and look up. The sky is a deeper blue than you've ever seen. The atmosphere is denser now, compressed by twice the gravity, clinging to the surface like a heavy blanket. Light scatters more aggressively through this thick air. Sunsets would last longer, burning through layers of orange and crimson that our Earth could never produce. The weather would be violent. A denser atmosphere means more energy packed into every storm system. Hurricanes would carry more force. Wind patterns would shift and intensify. And if this larger planet rotates at the same speed, the equator moves twice as fast, creating a stronger Coriolis effect that would spin storms into tighter, more powerful spirals. Now look at the landscape. Those mountains in the distance? They're shorter than you'd expect. On our Earth, the Himalayas reach nearly 9 kilometers. Here, gravity won't allow it. Rock buckles and sinks under its own weight. The tallest peaks would max out around 4 to 5 kilometers. Impressive, but nothing like Everest. The planet would look smoother, rounder, with wide plateaus instead of dramatic ranges. And the forests? The tallest trees on Earth reach about 130 meters. They're not limited by the strength of their wood. Wood is absurdly strong. They're limited by plumbing. A tree's vascular system can only pump water so high against gravity. Double the gravity, and that limit drops to roughly 60 meters. Every tree would be shorter and thicker, with massive trunks anchoring them against their own weight. Imagine a world of ancient baobabs. Wide, squat, powerful. The animals would tell the same story. No giraffes. A long neck pumping blood upward against 2G would require a heart the size of a suitcase. No graceful eagle soaring on thermals. At twice the gravity, the wing loading equation falls apart for large birds. They'd need wings so enormous they couldn't fold them. The skies would belong to small, darting creatures, hummingbird-sized flyers with oversized wings beating furiously. On the ground, everything would be low and heavy. Think rhinos, think hippos, think tortoises. Evolution would favor wide stances, thick legs, and compact bodies. A predator chasing prey at 2G would shatter its own leg bones on impact. Speed would be replaced by strength, ambush over pursuit. The whole rhythm of life, slower, heavier, closer to the ground. But beneath the surface, this planet is alive in ways ours can barely match. 8 times the mass means 8 times the radioactive material generating heat deep in the mantle. Volcanism would be relentless. Not the plate tectonic variety we know. This planet likely has a single unbroken shell. No subduction zones, no continental drift. Instead, massive shield volcanoes rising over permanent hotspots, bleeding lava for millions of years. The core would be searingly hot, and under these extreme pressure, something remarkable happens. Molten rock itself becomes electrically conductive. The planet would generate a magnetic field not from its iron core like Earth, but from a churning ocean of liquid magma. A shield against cosmic radiation built from liquid stone. So this world is harsh but survivable. Life adapted, civilization rose. And now, this civilization looks up at the stars and asks the same question we did. Can we go there? Here's where the story gets heavy, pun intended. Earth's escape velocity is 11.2 kilometers per second. Already brutal, you need to accelerate to 40,000 kilometers per hour just to break free. On this planet, the escape velocity doubles, 22.4 kilometers per second. And here's the thing about rockets. Doubling the speed requirement doesn't mean doubling the fuel. It means an exponential increase. The Tsiolkovsky rocket equation, the fundamental law of spaceflight, is logarithmic. On our Earth, a rocket headed to orbit is about 90% fuel by mass. The payload, the actual stuff you're sending up, is a tiny fraction riding on top of a controlled release of energy. On this bigger Earth, the fuel-to-payload ratio doesn't double. It increases by a factor of 10, maybe more. Chemical rockets, the kind that got us to the moon, would barely function. You'd need a rocket so enormous, so loaded with fuel, that it might collapse under its own weight on the launch pad. The engineering margins shrink to almost nothing. A civilization on this planet might invent physics, chemistry, mathematics. They might build telescopes and map the stars. They might dream of touching the cosmic ocean above them. And they might do all of that while being permanently trapped on the surface. Not by lack of knowledge, not by lack of ambition, by the simple crushing arithmetic of gravity. They would need to skip chemical rockets entirely and leap straight to nuclear propulsion, electromagnetic launch systems, or space elevators. Technologies we consider advanced. For them, they wouldn't be a choice. They'd be the only option. And here's the part that should keep you up tonight. Super-Earths. Rocky planets larger than ours are among the most common type of planet in the galaxy. We've confirmed over 5,000 exoplanets, and the data keeps saying the same thing. Earth is unusually small for a rocky world. Planets like Kepler 442b at 1.3 times our radius, or TOI 1243b at 2.3 times, they're everywhere. Which means across the galaxy, there may be countless civilizations who figured out the math, built the telescopes, and understood exactly what's out there. And then looked at their own gravity well, and realized they could never reach it. We got lucky, not because we're smarter, not because we tried harder, because our planet happened to be small enough to let us leave. So the next time you step onto a scale, appreciate that number. It's not just your weight. It's the difference between a species that touches the stars and one that can only watch them. If you had to live on this heavier Earth, what would you miss most? Running, flying, or the chance to leave? Drop your answer in the comments. Tune in and drift with us.